we're going to go over a couple of examples of how to use a velocity time graph to find acceleration and to make the corresponding acceleration time graph, and how to use a velocity time graph to find displacement. So in general, just as maybe a little review, remember that the slope of a line, so it says up here the slope of a velocity time graph's acceleration, the slope of any line is rise over run. It's change in the vertical axis variable divided by the change in the horizontal axis variable. So to find out the meaning of the slope of any line, rather than memorize what the slope of a position time graph represents and what the slope of a velocity time graph represents, to find the slope of any line, just ask yourself, what does the change in the vertical axis variable divided by the change in the horizontal axis variable represent? So in this case, the vertical axis variable is velocity. I look on this vertical axis, I see it's velocity. So in the horizontal axis variable is time. So the question is, what is change in velocity over change in time? And hopefully you recognize that's the definition of average acceleration. So we can find the slope of this line, we determine acceleration. Area under the curve, to ask yourself if the area under the curve has any physical meaning at all in a graph, because it doesn't always. Ask yourself if the product of whatever's on the vertical axis and whatever's on the horizontal axis has any physical meaning. Does velocity, that's our vertical axis variable, multiplied by time mean anything? And it does. So if I look at my equation for average velocity, this definition here, average velocity is displacement over time, so therefore displacement does equal velocity times time. When I multiply velocity times time, I end up with displacement. So it can be also helpful, if you don't know this off the top of your head, to look at the units and ask yourself, does the product of the units mean anything? So the units on the vertical axis are meters per second. On the horizontal axis, they're seconds, right? Those are the units for velocity and time. A meter per second times a second, I end up with a second over a second, right? And that's just 1. So I end up with this unit of meters, and meters mean something. So that's an indication, that's a clue that the area under the curve means something. So let's find our acceleration first. That's just the slope of the line, change in velocity over change in time. Before we do that, actually, let's just look at this graph in general and see what we can figure out without doing any calculations. I see that all these lines, or all the points rather, that this line is plotted above the horizontal axis, so that tells me that the velocity is positive. That's how we indicate direction. So let's say positive is to the right. Positive can be whatever direction you want, but let's just say it's to the right. This thing is moving in a positive direction. I also see that the slope is positive, and I know that's acceleration, so the acceleration vector also points in a positive direction. And we learn that when these two things point in the same direction, we have an object speeding up. And in fact, that's what we see when we look at the graph. At the beginning of this event, at 0 seconds, this object is going 0 meters per second. It's at rest. And then 3 seconds later, it's going 9 meters per second, which we can see here, right? And then 3 seconds later, it's going 18 meters per second. So this is going faster. As time goes on, this is gaining speed at a constant rate. So let's find the slope. The change in velocity is 9 meters per second. It goes up 9 meters per second. So I'll put that calculation up here. It goes up 9 meters per second in 3 seconds. So the slope, which equals the acceleration, is 9 meters per second every second. Is 3 meters per second every second, or 3 meters per second squared. I can make my corresponding acceleration time graph. I don't need a whole lot of points. It's constant for 12 seconds, so I'll put a 12 there to communicate that. And it goes at this constant acceleration of 3 meters per second for 12 seconds. That's what my corresponding acceleration time graph would look like. Now to find the displacement, I'm going to find the area under the curve. That's the area from the line to the horizontal axis. So it's going to be this area here that I'm outlining, and we can see that we have a triangle, and I know how to find the area of a triangle. So I'm going to find this area here, and I'm going to calculate it as 1/2 base times height. That's the displacement, and that's how you find the area of a triangle. So delta x is 1/2 the base of this thing. It runs 12 seconds across, so it's 12 seconds, and the height is 36 meters per second. That's its total change in velocity. 1/2 of 12 is 6. 6 times 36 is 216 meters. Make sure you put your units, and we see that the product of the units gives us meters too. So a second times a meter per second, so we have to always deal with units, does give us a meter, so this works out. Here's another graph. Let's see what we can figure out before we do any calculations. It's a velocity time graph. Check your axes. It's velocity and time. And we can see that the velocity here is negative. And a lot of people mess that up. You're used to these position time graphs, and you say, well, it's a positive slope, positive velocity. So you need to know what kind of graph you're dealing with. In a velocity time graph, if the line is plotted below the horizontal axis, the velocity is negative, and all that means is that it's going in some direction that someone decided was called negative. So it could say, instead of a negative velocity, we could say it's going to the left, or it's going up or down, or north or south, or back or forth. But negative just indicates direction. So it's got a negative velocity. We know the slope of a velocity time graph's acceleration. We can see that the slope is positive. That means the acceleration's positive, and for good measure, remember that also means that the net force, there's a constant positive net force. These things are stuck together. They always point in the same direction. So this would indicate when velocity and acceleration are pointing in opposite directions, it would indicate that an object's slowing down. And let's make sure that that's what we see here. It starts at 100 meters per second. It starts at negative 100 meters per second. When time is 0 and 2 seconds later, it's traveling at negative 80 meters per second. And this messes up people sometimes. And they think, well, 80 is, a bigger number, or negative 80 rather, is a bigger number than negative 100. So the velocity is getting bigger, but remember that negative sign only indicates direction. So we're just looking at the magnitude of these numbers. It goes from 100 meters per second to 80 meters per second. It is slowing down. So that's consistent with what we see when we look at at these vectors over here. Let's calculate the acceleration by calculating the slope of this line. Slope is just rise over run. What does this thing do? It goes up. It goes up by 20 meters per second from 100 to 80, and that change takes 2 seconds. Now, if you're wondering how this is positive, just a little reminder, if we're finding this difference, it's always final minus initial. So where did this 20 come from? I'll write it up here. We would have the final being negative 80 minus the initial being negative 100. And we know that negative 80 minus negative 100 is the same as negative 80 plus 100. So that's how we get plus 20. It always works out, right? So I just kind of did a shortcut and said, well, it went up 20. But if we actually do out this calculation, this delta V calculation, it works out fine. So this is plus 20 over 2. The acceleration is 10 meters per second every second. And it's a constant acceleration. So it's going at the same acceleration for all 8 seconds. So we don't need, again, to make this quantitative graph, I don't need to see a whole lot of points. For 8 seconds, its acceleration was a constant 10 meters per second. And there's that line. So that's done. Now we'll find the area under the curve. This is where, you can mess up a little bit because under makes you think you should go under the line. But remember, the area under the curve goes to the horizontal axis. So it's got to go to here. So it's this area here. And hopefully you can see in here I have a rectangle, which I can find the area of, and I have a triangle. I can find the area of that too. I'll call this delta x1. I'll call this delta x2. I'll find their areas, and then I'll add them up, and I'll know the displacement, the total displacement for this whole event. So the first area, delta x1, is, put it down here, is just a rectangle. So that's just going to be length times width. It goes 8 seconds across. It goes negative 20 down. 8 times negative 20 is negative 160. The unit's meters, and I would know that because I'm calculating a displacement. I also know that because the product of the units gives me meters. A second times a meter per second gives me a meter. Find that second area. This is a triangle. This area 2 here, it's a triangle. The area of a triangle is 1/2 base times height. That base is still 8 seconds. This is the base. It goes from here to here, and it runs from 0 to 8. So the base is 8. And the height, it goes from 20 to negative 100, so it's negative 80. 1/2 of 8 is 4. 4 times negative 80 is negative 320. I add this together, and I get negative 480 meters is the displacement. So what does that mean? It means that this object started somewhere, and I don't know where. I'm given absolutely no position information here, but it starts somewhere. And if we say this direction's negative and we say this direction's positive, it starts wherever it starts. Let's say it starts here. And it moves around, and we can actually see from the velocity time graph that it does move in the same direction the whole time. It's going in a negative direction the whole time. At the end of this event, 8 seconds later, the object is here. It moved 480 meters in this negative direction. I don't know what these positions are. So it could still have positive positions. It can have negative positions. I have absolutely no idea. All I know is that from where it started to where it ended, it went 480 meters in a negative direction.